So continuing on with asking what happens when I square this operator. The square of an operator simply means to multiply it by itself, which corresponds then, as you can see, to simply applying the operator in sequence twice. Now, we know what the parity operator does to f of x. That just changes it, by very definition, to f of minus x. And the really tricky part here now is what happens when I apply the parity operator to f of minus x? Now, the answer to you may well be kind of obvious, but that's because this particular operator is particularly simple. Right? I want to show you how you should properly think about this to avoid confusion that can really mess people up. It really is a common source of errors when you're dealing with more complicated symmetries. Remember what I had told you. This definition, what it really means is everywhere I find an x, I replace it with minus x. So when I look inside this function, f of minus x, I'm going to put some extra parentheses around the x. It's the x that's buried inside those parentheses where I'm supposed to apply my minus sign. Technically, I don't just apply it inside the outer parentheses of the function. I'm supposed to apply my mathematical operation to the x's that exist inside my function. So when I do that, then I see this will be f of minus, and then what gets replaced in the brackets around the x is it gets replaced with a minus x, which then, of course, is probably what you had been anticipating anyway, but we've done it now the safe, mathematically correct way, so that now we can safely say and simply see we get back our function f of x. So that's very neat. So this parity operator is particularly simple. Its square, as you can see, corresponds just to what we would call the identity operator, right? It just gives us always our function back again. So we can write that a little more abstractly as saying that p squared equals, and I like to call the identity operator 1 hat. This is the identity operator. Some people like to call it I. I personally start to get confused then with the square root of minus 1. So I like to call this 1 hat, but it's defined so that the action of 1 hat on any function f of x is, well, just to multiply the function f of x by the number 1, which of course just means it always gives me back f of x. It's the identity operator. That's kind of interesting. Now, here's another one we can ask ourselves. What is the inverse of the parity operator? What would that be? Well, if we think a little bit about what the inverse of an operator is, the inverse of an operator would be something so that if I multiply my operator by its inverse, or in other words, I could write it like so, this simply means apply the operator, right? And then the next thing you should do is to apply the inverse of the operator. But the job of the inverse of the operator is to undo the action of the operator. So by definition, the inverse is defined so that this product is 1. And if we compare this equation with this interesting property that p squared is just the identity, we can immediately pick off that, well, the perfect thing to multiply p by to undo its action is p. So in fact, we learn that the inverse of this parity operator is just the operator itself. Now, those are some of the algebraic properties of an operator. There are other questions in quantum mechanics that we always want to ask ourselves when we have a new operator. One quick one, I don't want to spend the time to prove it, but you can ask yourself, is the operator Hermitian? Right? Look at the hermiticity property. And in fact, yes, P is Hermitian. You can prove that, prove it on your own. Basically, you write down the Hermitian inner product, and you change, and what you want to do to prove it is you can change your integration variable in the Hermitian inner product from x to minus x, and that will actually give you your proof that it's Hermitian. So we have hermiticity. Now, the other question we like to ask ourselves in quantum mechanics is, what about the pure states? The pure states of an operator always tell us something interesting about that operator. So let's consider the pure states. So that would mean I apply the parity operator to some generic function, right? And what I get back again, if it's a pure state, the quantum purity test is also known as the eigenvalue equation, right? That's where I apply my operator and I get back my function back again completely, except for some prefactor, which is just some complex, in general, some complex number. If it's Hermitian, we know it's going to be a real number. But the point is, this is just multiplication by some number. Now, we can actually say a lot about what this number has to be because of this interesting property about the square of the parity operator. So let's apply that then. So p squared on f of x, then, if I have a pure state, well, for any state, it's p applied to p acting on f of x. But because this is pure, I know I can replace this inner operation with p times f of x, because it was a pure state. And when I make that replacement, the number p, because p hat is a linear operator, can be pulled out of the operator. That gives me p multiplying p hat applied back to f of x again, which of course then gives me p times f of x. So we suddenly learned that p squared acting on f of x gives me the square of the number p multiplying f of x. But previously we knew that p squared acting on f of x is in fact just f of x. And for this equation to be true, there are only two possibilities. Either p squared equals 1, or, of course, the only other way this could be is that f of x equals 0 everywhere. But that would not represent any kind of quantum state of interest to us. That's the trivial function, right? Anytime I have an eigenvalue equation, 0, of course, will satisfy it on both sides. We're looking for non-trivial solutions. This can't really represent a state of a system because it's not normalizable. So I must conclude then that for any pure state, p squared equals 1. So there are two types of pure states for the parity operator. So we have either parity equals plus 1, which tells me then that parity operator on f of x equals 1 times f of x, or just plus f of x back again. But recall that the parity operator on a function is just f of minus x. So if we have this mathematical relation, we learn that if the parity value is 1, the pure state of the system then is an even function. Very nice. And you very well may see that the other case that we have is that p equals minus 1. I can follow the same logic. P of f of x then, which I know from the action of the operator p, must be just f of minus x. But from f of x being a pure state, if it is a pure state of parity, then the action of p on f of x is also just to pull out a minus sign, giving me minus f of x. So we could have then, if we have a pure state, we would then have an odd function. So the conclusion then is that pure states of the parity operator are either even or odd functions. And that is very interesting, because what this seems to be telling us is that there must be something about this parity symmetry and how it interacts with my finite square well, which somehow ensured I should have been able to guess somehow that because of this parity symmetry, that the eigenstates of my finite square well, that the pure energy states, must also have turned out to be pure states of the parity operator. So now we can go back to our general considerations and ask ourselves, what is it about the Hamiltonian operator that would make it so that the pure states of that Hamiltonian operator would also have to be pure states of the parity operator. And that's a very general type of question I can ask for any symmetry and any associated symmetry operator. So now we're going to go back to our more general discussion, hoping we can find out why it is that pure states of our finite square well Hamiltonian had to also be pure states of parity.